This particular video, we have some unknown mass is attached to a spring with the spring constant 75 newtons per meter, and then it is allowed to oscillate, and the velocity versus time graph is given to us here. So let's go and crack out A, B, C, D, E, F. If you need to, pause it. So the first thing I do want to point out is that the velocity here is given in centimeters per second. So if you like, I would encourage you to convert centimeters per second to meters per second, unless the question keeps it in centimeters or centimeters per second. Okay. All right. So let's go ahead and do A, B, C, D on this particular slide. Now, part A asks us to find the period of the oscillation. So in order to find the period, you figure out the time for one cycle to happen. But the first thing I noticed in this particular graph here is that the author goofed on this one. Probably not intentional, but probably just accidental here, I hope. So if you please keep up with counting here. So the first line that's dark here is 0.2. Therefore, every increment or the interval here on the horizontal axis should be 0.2. So it'd be 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, and this red line that just came up, that should be 1.6. However, the author presented 1.6 to the right of this red line, which is incorrect. Okay. So keep that in mind. Again, I'm not sure if this was intentional or just a mishap. All right. But other than that, the red line is 1.6, not this 1.6 given in the printed diagram. All right. So in order to find the period, all I have to do is go from crest to crest here, or from peak to peak. That is one complete cycle, or a circle, and that right there is 1.6 seconds, once again, because every increment here on the horizontal axis is 0.2. Okay, so I'm just going to shift the 1.6 here, draw on here to just where my red line is. So therefore the period for this one is just 1.6 seconds. All right, part B asks to find the frequency. Frequency is just simply 1 over the period. Well, I just found what the period is just simply by looking at the graph, which is 1.6 seconds. So from there, I can just do a little plug and chug. It'd be one cycle divided by 1.6 seconds, and that will give you an answer of 0.625 hertz. All right, or s to the -1, depending on how your professor or teacher wants it. But I'm just going to write hertz. Frequency is often measured in hertz. All right, let's do part C. Part C asks us to find the angular frequency. Well, to find angular frequency, I know the function for angular frequency is 2 pi rad divided by t. 2 pi rad because every one cycle is measured in period of time known as capital T. So here I know what capital T is based on the graph. So really it's just a plug and chug. 2 pi divided by capital T, which is the period, as I identified earlier, is 1.6 seconds. If you reduce this on your calculator, you get 3.93 rads per second. All right, so that's the answer for part C. So far A, B, and C are pretty light work. All right, the other way to do angular frequency is simply doing 2 pi times frequency. So therefore 2 pi is carried over, and then the frequency, which I found in part B in purple, so frequency here is 0.625 hertz. I can simply substitute out F for 0.625 hertz, and if you simplify 2 times pi times 0.625, that'll give you the same answer of 3.93 rads per second. As you can see, there's a couple different ways to find part C if you like. Okay. All right. Part D asks us to find the amplitude, and at what time does this reach this position? Well, in order to find amplitude, I think for this particular graph, the easiest way to do it is simply just use V max equals A times omega. Well, why do I want to do this? Because one, I know V max from the diagram. V max is given as 20 centimeters per second. Once again, if you convert it to meters per second, it's be 0.2 meters per second. And then omega here is we already found in part C, which is 3.93 rads per second. So in order to find A, I'm just going to go ahead and divide both sides by omega. And then here I know values. V max I can pull from the graph. Once again, the graph here in the vertical axis is centimeters per second, but I can just convert 20 centimeters to meters. That would just be 0.2, because I'm just going to take 20 divided by 100, because for every for every meter there's 100 centimeters. Okay, so I'll convert that centimeters of 20. I'll convert 20 centimeters per second to meters per second, which is 0.2 meters per second, and then omega we already found, which is 3.93, and I'm going to simplify that on my calculator. That'll give me an amplitude of about 0.051 meter. That's the answer for part D. Okay, and then the second part of part D asks us, at what time does the mass reach this position, aka where does it reach the amplitude? Well, I know it reaches the amplitude when velocity is 0, because that would imply that the object is being stretched to the far right or compressed to the far left, which means it has not been released yet, which means it hasn't moved yet. So in this particular case, if you look at this graph here, watch my follow my cursor. This is a velocity time graph. Well, where is velocity 0? Velocity is 0 right where my cursor is. That would be 0.4. And if I keep going to the right as a function of time here, the velocity is 0 again at about 1.2. And then if I keep going, the velocity is going to be about all the way to here, which is actually about 2. Okay, so I remind you that the interval given here is a little off. So it'd be 1.4, 1.6, 1.8, and then 2 will give you back where v is 0. So my answer is going to be 0.4, 1.2, and then 2 seconds. So that is the second part of my answer for part D. Let's go ahead and do E and F. Part E here asks you to find the maximum acceleration and then the times at which it occurs. Well, light work. The function for A max is A omega squared. We already found A, we already found omega. A we already found previously as 0.051 meters, and omega we already found previously as 3.93. I'm going to square that and really just calculate the work time. If you do this correctly, the magnitude of the maximum acceleration is 0.788. And then again, it can be positive or negative based on whether the spring is being compressed or stretched. Okay, so the value I give you here is just simply the magnitude. All right, so that's that. And then let's see. It asks you also the times at which this occur. Well, A max occur where v is equal to 0. So there's v is equal to 0. There's v is equal to 0. Okay, and then there's v equal to 0. Yeah. So A max occur where v is equal to 0 because when you pull the system to the extreme right, well, that's where maximum acceleration occurs because it's a function of x, or it depends on x, but then you haven't let it go yet, so therefore v is 0. Okay, so these are relationships you should keep track of. A max occurs where v is 0. So these are the location where v is 0. So if I counted correctly, this would be 0.4, the 1.2, and once again to the very end here is actually 2 seconds. Hopefully you've been listening. All right. So the second part of part E is 0.4, 1.2, and 2 seconds. All right, so it'd be half of a cycle each time. All right. Part F asks us what is the mass of this particular system. Well, there are a few ways to do it. I'm just going to show you a couple different ways here. If you know the expression for a period in terms of m and k, you can find period using 2 pi times radical m over k. But here you're asked to find mass, so I'm just going to square both sides. Just get rid of this radical sign in order to get m by itself. So t squared, and then 2 squared is going to be 4, pi squared is going to be pi squared. And then I just want to move that term to the left side by dividing both sides. And then the only thing left on the right side is m over k. So keep in mind, squaring cancels out the radical sign, okay? Well, I don't have m by itself yet, so to get m by itself, I need to multiply both sides by k. So I'm just going to move the k up to the top left. So it'll be t squared times k divided by 4 pi squared. And then really here I know everything. Period is extracted from the graph earlier, which is 1.6. I'm going to square that. K is given in the statement here at the very, very top of the screen, 75 newtons per meter. And then 4 pi squared is just a constant. So if you simplify this all on your calculator, you should get a value of about 4.86 kilogram. So that's the first strategy. Now, it all depends on how you see these particular harmonics problem and what information you can pull out, quickly. Well, the other way you can do it also is to set up the Hooke's law equals to net force. But here, I'm just going to leave out the negative sign because Hooke's law has a negative sign. I'm just going to leave the negative sign because I'm just trying to find the value of m, which being a scalar anyway, so the negative sign doesn't really matter, okay? So here, it'll be kx, but instead of x, I plug in k, a for amplitude. Well, if I'm going to use a for amplitude, then I know that a is a max because that's where maximum acceleration occurs when you pull the system to the very, very far right, and that distance is known as your amplitude. So here to find, what is it, m, I'm just going to divide both sides by a max. So m is equal to k times the amplitude divided by a max. Well, I know what k is, which is given as 75. A I already found earlier, which is 0.051. And then a max here, I just found to the left side of the screen here is 0.788. So really, if I plug and chug, you'll get the same answer. Okay, I'm running out of room on my screen here, but you can check my word for it. I actually punch it in my calculator, and I got the same value of 4.86 kilogram. So again, there's different ways to find quantities here in harmonics. It's up to you how you interpret these information and what you can pull out quickly. All right, stay nerdy, don't be whack.